Hello to all my petroleum engineers, friends all over the world. I have been asked many times about the origins of the rig hydraulics equations and how I came about them and how I derived them. Well, I derived those equations a very, very long time ago. And so in this short video, I'm going to share with you very quickly how these equations were derived. If I were to go through the whole chapter, that would take about a week at least. So what I'll do now, if you don't mind, I will only share with you some of the ideas, and hopefully the chapter is there for you to read, and you will learn from it. Okay, it's quite straightforward. So I'll share with you the fundamentals. If you don't mind, there are a number of videos which may be of interest to you. So I've given you these links. I don't know if you can see them, YouTube and our Facebook and also our website. So to start with, when we talk about fluid flow in pipes, we really need to understand some fundamentals like viscosity. What is viscosity? Also, we need to talk about shear stress, as defined by force over area, of course, and shear rate, which is the change in velocity over a distance. And the two things are related together by what we call viscosity. So this is all explained here. And the most important thing for you guys is to understand that viscosity has a unit of poise, and poise is a very large unit, so we use centipoise. And it shows you how we derive those in the various metric and the imperial system. Imperial system meaning the oil field units. And then I go on to talk about the types of flow. In drilling, we have laminar flow in the annulus usually, and turbulent flow in pipes. Okay, but we need to know, because sometimes even inside pipes, the flow is actually laminar. So how do we tell? We have to have a criterion for type of flow, and the criterion is to use what we call Reynolds number, and this depends on these factors, which are the diameter, velocity, density, and viscosity. And here I show the how we converted the Reynolds number into the field units, because obviously this is consistent units. In other words, let's use the pure metric system, and we need to convert it to all field units. So by doing through all this simple manipulation, you end up with Reynolds number equals 15.46 diameter, velocity, density over viscosity. So that's very important to remember how this came about. And then we talk about types of fluid, Newtonian and non-Newtonian fluid. We don't actually have Newtonian fluid in drilling, mostly non-Newtonian fluids. And we have two types of those fluids which we normally use, the Bingham plastic model. And this basically shows that the shear stress is equal to the yield point, similar to steel, you have a yield, plus plastic viscosity times the shear rate. And we can replace the shear rate by the change in velocity divided by the distance. You can see here I put a negative sign to indicate that the velocity of the fluid decreases as you move away from the center of the pipe. So the velocity is maximum in the center of the pipe normally. And then the power law fluid, it has constants K and N, and these are described here. And once again, you have a minus sign. Very important, you include the minus sign, otherwise the equations will not be correct. And then we talk about viscometers. These are the fan viscometers, how we measure the viscosity. Viscosity has many, many different units and can be expressed in various ways. But the ones you need to understand in the oil industry, two things: a plastic viscosity, okay, which is equal to theta 600 minus theta 300. Theta meaning the torque reading at 600 RPM. So you rotate the viscometer at 600, and a 300, and the difference between the two readings will be the plastic viscosity. And the yield point will be simply theta 300 minus plastic viscosity. So these are the fundamentals. And then you need to come to derive the flow equation. So you start off, first of all, with the laminar flow. And with the laminar flow, it can be Bingham plastic or power low fluid. So if we go for the Bingham plastic, we start off with the pipe flow, and we have annular flow. So this is quite simple, really. The deriving these equations. You can see if you go through this, they're not very difficult at all. And by continuing through these simple derivations, okay, and remembering, of course, to use the actual plastic model for your basic concepts, and you do a little bit of integration. And so most of this integration is basic second, third year university. And as you continue, you come up with an equation like so. Now, the first thing you notice is that this equation is not familiar to most engineers, so we need to convert it into field units. And you need to learn how you do that, because if you come up with a new equation, you need to learn the technique. And here I've shown you the technique, how you actually take an equation and convert it into field units, because all your equations of reservoir engineering, production engineering, drilling, anything, they have been converted for you into field units by somebody. So here I'm doing these for you. So you look at this equation and you see how I converted those into imperial system, i.e. the PSI and foot and whatever system. So if you continue with the conversion, you come up with the equation which is familiar to most engineers. So this is the pressure drop in pipes, laminar flow using the Bingham plastic model. But we need to know if the flow is actually laminar or turbulent. So we have to find out a criterion, and the criterion is Reynolds number. But because Reynolds number is cumbersome to use, so what I decided to do is to use a critical velocity, because in drilling we always calculate velocities. So my principle here is to find a velocity that causes turbulent flow, and I called it critical velocity. Okay, so what I do, I go back to Reynolds number and say, what is the critical velocity that will cause turbulent flow? So in this case, I need to make an assumption, what value of Reynolds number? And from my experience and the work I've done, and I've spoken to a number of people, usually you have fully turbulent flow at 3,000. Some people say 2,600, 2,800, but really for fully turbulent flow is 3,000. So if you put 3,000 for Reynolds number and you continue the derivation as we did before, you come up with an equation for the critical velocity. So the critical velocity in the imperial system is given by here in foot per minute. Okay, and so you calculate the average velocity in the pipe, and you calculate the theoretical critical velocity. So if the fluid flow using your normal flow rate, let's say 600 gallons per minute, gives you a value of say 100, and the theoretical critical velocity is 200. Therefore, your velocity is actually less than the critical, so the flow is laminar. So the critical velocity must not be exceeded. If it's exceeded, then the flow is turbulent, and you can't use these equations. So that's the principle. And we do the same thing for annular flow. So annular flow, you consider two pipes, because obviously the circular pipes would be difficult to model because of the curvature. So we assume them to be two plates. Okay, and we carry out exactly the same work as we did before, except in this case we have difference in diameters rather than a pure inside diameter of a pipe. And if you continue with the same method as you did before, continue with the derivation, and then you get a little bit of integration, and eventually, of course, you come up with an equation like this. Very nice equation, but you need to convert it into a field unit, as we said before. And it looks horrible, but that's the one we use in PSI. So that is the flow to calculate the flow equation to calculate the pressure drop in the annulus if the flow is laminar and obeys the Bingham plastic model. It's a difficult equation to say, a difficult sentence to say, but it has to be said like this. So annular flow equation in laminar flow obeying the Bingham plastic model. That's how it should be said. And I've given you here an example of how you do the calculation. You find the critical velocity and you find the average velocity, and you compare the two, and you know the flow is laminar, therefore you can apply this equation. If it's not laminar, you cannot apply this equation. Okay. And if you go now into the power law model, the power law model is slightly more complex in terms of mathematics, but it's still the same principle. Nothing's difficult. In the power law model, we have the shear stress in terms of consistency index K, shear stress, and then the flow index N. Okay, and a little bit of log work, which is really first year university. Okay, and then a little bit of integration. I'm not going to go through this because you can read it. And if you continue with the simplification, you end up with a very nice equation here, which gives you the pressure drop in pipes, assuming the flow is laminar and obeys the power law model. You can see, so it's quite a mouthful. Okay, and I've shown you how you do the conversion for the field units and for the metric units. So I'm not going to go through that. And you do the same thing with annular flow. Again, you use the same principle, except now the diameter will be the difference between the hole size and the pipe OD, because that's where the flow in laminar occurs. And you continue with the integration as before, and you end up with a fairly simple equation really to calculate the pressure drop. So here showing it to you in bar, and you can also see it in PSI. But before you can use this equation, you have to ensure the flow is actually laminar, not turbulent. So again, you need to calculate the critical velocity for the power law. And once again, you repeat the same process. And I've done this in a great detail so that you see how they come about. They're quite simple. So I've never seen these equations derived in this way and in this great detail, but I did them so that people can see they're quite simple. So if you continue, you end up with the critical velocity using the laminar flow model. Okay, it's for power law. And here showing you the conversion into field units. Now we're going to come to turbulent flow. So if your critical velocity is calculated above, shows that the flow is turbulent. In other words, your average velocity, which is Q divided by area, is 200 and your critical velocity is 100. So obviously, the average velocity is more than critical, so the flow must be turbulent. That can be quite hard, actually, and difficult to calculate. So simplistically, we use this equation, which was derived a very, very long time ago, and it depends on the friction factor. So this equation is quite simple. It just depends on the length of the pipe, the average velocity, and the diameter, and of course, there's density. But you can see it contains F, the friction factor, and that is quite a difficult term to calculate. So I looked at a number of references, and to this date, the best reference was the Blasius, which is also used by Schlumberger, okay, which says that the friction factor is equal to 0.057 times Reynolds number raised to the power minus 0.2. Okay, there are other correlations, but the difference in answers is very, very small for practical purposes. And what I mean, when you get answers like plus minus 2 or 3 or 5 psi or even 10, they are negligible because you cannot read them on pressure gauges. So if we use this factor and then we go to the Reynolds number is given by this rho VD divided by viscosity, and you plug that into the friction factor. So now the friction factor is expressed in terms of velocities. And if you plug that back into this equation 546, that is actually the turbulent flow equation. And then if you simplify this further, okay, you end up with the equation which you've seen in my book. So this is the final equation in bar, and this is the final equation in PSI. So it's 8.9 times 10 minus 5, density 0.8, Q 1.8, PV 0.2 times L divided by diameter of the pipe, inside diameter 4.8. So this is the equation for turbulent flow inside pipes. Okay, so you can see the only difficulty with this is the use of the value of the friction factor. And the friction factor will only affect this value. So sometimes you see it as 9.1, 9.2, sometimes it's 8.4, but really the difference is very, very small. Okay, and then for annular flow, so if the annular flow is turbulent, again, you use the same principle, and you end up with the equation in the metric system, and here in the imperial system. There's an L missing here, which I put in. Okay, so and finally we go through the flow through nozzles, and we use Bernoulli equation. So we compare the flow and the amount of the fluid at the top of the nozzle and at the bottom of the nozzles, and we come up with what we call the nozzle velocity. So the nozzle velocity is given by 1.344, the pressure drop across the nozzle divided by the density. Okay, and here I use what we call a discharge factor or correction factor, because most derivations assume there is no frictional loss inside the nozzle, because the nozzle is very, very small. But really, you got to allow for a minute loss, which is so I put a factor of 0.95 to allow for this. So that's why some of my equations slightly different from some of the equations you see in textbooks. And once again, if you convert this into field units, you see the nozzle velocity 33.358 square root delta P divided by rho. And you see the nozzle velocity expressed in foot per second because it's very high. Okay. And we can derive from this equation the nozzle area using the equation Q equal VA. So this is sort of inverted, and this is the area of the nozzles, and the diameter obviously is related to area. So that is a fraction of an inch, and normally we have nozzles expressed into a size expressed as a fraction of 32. So an open nozzle will be equal to 32 or 1 inch. Okay, so to find the nozzles in multiple numbers, we simply multiply the result here by 32. So any fraction will be removed. So if you get 0.1, sorry, if you get say 0.2, so 32 times 0.2, you would get 16 point something. Okay, so we get rid of the fractions and we get the nozzle size in terms of 16. So that will be 3 nozzles for a 3-bit nozzle. Okay, and here's an example which shows you how to do the calculations. And then finally, of course, I give you some references where I got some of these equations, and there's a problem for you to play with. Once again, don't forget to visit our sites and what we do. And thank you for listening to me. Thank you very much.